Now that we've learned about functions, we get to compare them. So let's take a look at our first example problem. Josh and David are driving to Josh's house in separate cars. They both start 160 miles away. So it's pretty far away that they're going to be starting. Compare their functions below and determine who drives to Josh's house faster. So here we have Josh's function. He starts at his 160 miles away and gets to his house in 4 hours. And the way that they have this graph drawn is it's how many miles away from his house he is. So that's why the graph goes down. Over here, we have David's function, and we have it in a table. So we can see how many hours passed and then how many hours he's actually traveled, getting to that 160 mark at 4.5 hours. Now, there's a couple different ways that we can compare it. We can either find what their rate is and actually compare who's driving faster, or we can think about the fact that David's getting there in 4.5 hours, where we know that Josh is getting there in 4 hours. So logic would tell us the person getting there first is going faster. So since Josh is getting there first, he is going faster. And that's really how we compare functions. We're just comparing the data with another set of data. Let's take a look at another example. Here we have another set of data that we need to compare to each other. So we have the question, which bus type can hold the most people? So here's the function of bus A. And it's telling us that 2 buses of bus A can hold 80 people, 4 buses can hold 120, and 5 buses can hold 160. Then we're going to compare that to the function of bus B. So for bus B, 3 of those buses can hold 90 people, 5 of those buses can hold 150, and 6 buses can hold 180. So we just need to see how much one of each can hold and then compare them to each other. I'm actually not going to work through this one. I want you to try it on your own. And if you have questions, you can come ask me in class, or you can comment in the comment section. So now we're going to take a look at the notation that goes with function. I could have taught you this a couple lessons ago, but I wanted you to get comfortable with functions before I sprung this on you, because it always tends to look a little scary. So the notation you normally see with functions is this, f parentheses x. And the way we read that is f of x. Okay, so it's a little funky, but if you receive that, you would read it as f of x. And what this represents is it essentially is just the y value. So when dealing with functions, a lot of times you'll see that f of x, just replace y. And that's really all it will mean. So let's get down some examples of ways that you'll see this. So let's say we had this equation, y equals 2x minus 4. Now if we're talking about it from the perspective of a function, you'll just replace the y with f of x. And so that would look like this. So what this represents is the function of x is 2x minus 4. It's telling us that this is how x works. Another way you can see it is if we have a graph. So let's say we had a graph, and this side, of course, is x. Well, instead of calling this side y, you might see that side called f of x. So really it's just replacing y. Same thing with the t-table. So we have x as normal, and we might have the f of x on the other side, replacing where y would have been. And then, of course, we could have values in there. Now, the normal notation is f of x because we like using x in our equations. But technically, it's just saying it's the function of whatever. So let's say I had an equation that didn't use x. So in this case, it's saying the function of g is all of this stuff because we're dealing with g instead of x. And you, of course, can kind of replace any variable that you're using in there because we're saying it's a function of whatever's going on. It's a function of this situation. We're going to take a moment to go back to linear and nonlinear just to get it straight in our heads of how to tell which is which as we go forward. So you might remember that linear means that when we graph it's going to be a straight line. This definition, of course, makes sense because linear has the word line as the first 4 letters. Now, nonlinear, of course, when you graph, it's not going to be a straight line. So these definitions are all good and wonderful, but what if I want to tell something's going to be linear or nonlinear without graphing it? Because graphing's a pain. Well, you might remember from the lesson way long ago that nonlinear things are going to have exponents. They're going to be squared and cubed and stuff like that, whereas linear is not going to have any of those. So these might be some examples. X squared, it has an exponent, or 1 over x. You have to remember that actually equals x to a negative 1, or x to a negative fifth. Same thing. It's going to have those exponents so that you're going to get kind of a weird, funky graph coming out. Whereas if you have none of these and you just have a nice little equation with no exponents, then it's going to be a nice straight line. So now we're going to look at how we use functions and how we might write functions. So here we have the example. Write a function that would describe how to find the area of a square. Now, it's been a while since we've done area, so I always like just drawing a picture because it gets our mind going. So here we have a square, and the area is the stuff in the middle, okay? Now, remembering back to, I can't even remember when we learned this stuff, we remember that areas is going to be this side multiplied by this side. So let's call, I don't know, this side x, and this side, because it's a square, should also be the same length. So it's also x. So area is going to be x times x, which we know x times x, of course, is just x squared. So the function of the area, the f of x, of area is going to be x squared. And we don't actually have to solve anything. That's it. Now then it asks us, is this linear or nonlinear? Well, we just reminded ourselves that if there's exponents, it's going to be nonlinear. So we can go ahead and say that's going to be nonlinear because it's squared. Let's take a look at one more example. Here we have an example that's extremely similar. We have to write a function to show how to find, oops, that should not be area, that should be volume of a cube. Because cubes, of course, have volume because they're three-dimensional. Something like that. So because there's 3 dimensions, you're going to need to be multiplying each side together to get that volume. Now, I'm actually not going to go through all of this. Hopefully you can look back at the one we just did, since it's fairly similar, and figure this one out. So you need to write a function that describes how to find the volume of this cube, of just a generic cube, maybe with the side of x, and then you're going to tell me if it's linear or nonlinear. If you have any trouble with this one, you're of course going to ask me during class or comment in the comment section. And that is it for this lesson.